Aloha, we are Team Hokulele and today we'll be presenting our 2020 to 2021 project.
Team Hōkūlele is the University of Hawaii's first high-powered rocketry-based vertically integrated project and senior design team. This summer we plan to launch our first two-stage rocket, which will carry an inert camera payload and a radio-controlled rover payload in the 30,000-foot category at the Fortune 30 competition on June 5th.
The team has been organized as shown in this diagram, with senior design members serving as leads for each subsystem.
The rocket is first prepared for launch on the launch pad. Once ignited, the rocket takes flight until the Stage 1 motor burns out and drag separates, which causes the first stage to deploy a parachute, while the Stage 2 motor ignites. Once the Stage 2 motor burns out, apogee is reached and the avionics trigger the deployment of the drogue parachute. Once the rocket reaches 1,500 feet, the avionics trigger deployment of the main parachute, which ejects the payload canister. The rocket continues to descend under the main and drogue parachute. The payload canister will open when it reaches ground level, and the rover will deploy and travel at least 10 feet.
Here's our design of our 2020 to 2021 two-stage rocket. The top picture shows the overall design and dimensions of the rocket, while the bottom picture shows the rocket on the program Open Rocket, which was utilized to design the rocket and simulate the flight of the rocket.
For propulsion, we've decided to use the N3300R motor for both Stage 1 and Stage 2 to allow our rocket to reach an apogee of 30,000 feet. Using the Open Rocket simulation with the weather parameters at the far side, the rocket is projected to reach an apogee of 28,500 feet in approximately 47 seconds.
This year's fins are a clip delta design with a 45-degree chamfer at the leading and trailing edges. The chamfer creates a double diamond cross-section which allows the fins to be more aerodynamic. The figure on the left shows a console simulation of the temperatures the fins will encounter during flight.
This year, we decided to incorporate a parachute reefing panel to reduce the opening shock that the parachute generates upon deployment. The slider will cause a slight delay in parachute inflation as it moves down the suspension lines and will rest at the base of the parachute, causing an increase in drag and lower descent rate.
The Rover is a two-wheeled model capable of traveling a distance away from the landing site while transmitting live camera footage and RC controls to and from the ground station. It will be controlled using the Arduino XY remote application on the Rover operator's mobile device, which is connected to the transmitter via Bluetooth. This transmitter relays long-distance directional input to the Adafruit Feather microcontroller that manages the wheels of the Rover. Each wheel is connected individually to a stepper motor that rotates depending on the directional input it receives.
One of the payloads that the rocket will be carrying is an inner camera array, which consists of two cameras, an action or SD camera to document the entire flight process, and a first-person view camera to transmit the live footage.
The rover will be deployed with a treasure chest method, where the capsule will open as a hatch. The hatch will only open after the payload is landed, and the altimeter reads an altitude within the range of the initial altimeter reading. Once this requirement has been met, the actuators will activate, opening the hatch as seen in the image on the right.
As shown in the slide, this is the two-stage rocket's structural components that have been completed as of spring 2021. On the left is the two-stage rocket component split into 4 sections, and on the right is all the structural components which is assembled as one system. The Stage 1 and 2 motor assemblies and nose cone were completed by the 2019 to the 2020 team before manufacturing was put on hold due to COVID-19. The 2020 to the 2021 team has picked up where the previous team has left off and made some improvements and changes to account for the new fins and rover payload. The nose cone tube and the circular body tubes are made out of fiberglass, while the tip of the nose cone is made out of 1080 steel. The fully assembled rocket is roughly about 15 feet long in length and 6 feet in diameter. The structure of the rocket is built to withstand high-speed flight and to contain the interior components of the rocket, such as the payload, avionics, and rocket motors.
The fin frames are made of ABS M30 3D printed filament, which are then covered with an epoxy carbon fiber shell to increase their structural integrity and prevent fin flood during flight. Both materials are lightweight and can withstand the forces and temperatures encountered during flight. First, 2 sheets of carbon fiber were laid on the top of the fin, then epoxy resin was applied. This was followed by peel ply and breather fabric. The fin was then vacuum bagged and cured overnight. This fin assembly reduces the overall weight of the fins compared to last year's design.
After the curing process, a test fin and through-wall fixture similar to that on the rocket was manufactured. A bend test was performed to ensure structural integrity of the fins. No visible deformation was noticed, so the fins passed the test. The fins were finally attached to the body of the rocket and secured by epoxy fillets. A final layer of carbon fiber was applied over the entire fin set and body tubes, which completes the fin manufacturing process.
The images on the left are the components of the payload deployment canister. The canister body is made of a fiberglass cylinder with a sidewall cut out. The sidewall will be hinged back to the body to act as a chest door. The circular wooden discs are marine plywood bulkheads that will be epoxied to both ends of the main body. The images on the right are the result of a 2-meter-high drop test. The damage from the test was analyzed and used to help update the rover design.
The static motor test was conducted on March 20th at Windward Community College. The purpose of the test was to learn how to assemble the motor, test the structural integrity of the rocket's body, and to obtain a thrust curve from the motor used. The Pyrotechnics and parachute deployment test was performed multiple times to test if the chutes and payload canister would emerge. This also acted as a pre-run for preparing the rocket for launch and checking continuity between the pyro charges and the avionics bay.
In conclusion, the goal of Team Hōkūlele are to compete in the Friends of Amateur Rocketry 1030 competition on June 5th, 2021. The second goal is to test the first iteration of the two-stage rocket and payload. And thirdly is to teach the VIP team member the basics of modern rocketry. Some benefit of joining Team Hōkūlele are getting rocketry certification, networking with professionals at competition, and learn hands-on in the field of aerospace engineering.
Please contact us if you're interested in learning more or sponsoring our team. Thank you.